Queria pedir o silêncio de todos para a gente iniciar a nossa programação.
Hi, Priscilla. Hi. Yeah. Hi. Hi. No, just hi. Yes. If you can find a seat, we're going to get started, please. Have we learned the code? What's the code here? Have we learned this yet? We're not. You can't hear me? Okay. I will lean in. So, good evening, ladies and gentlemen, distinguished guests, and fellow space enthusiasts. Welcome to the ISU, International Space University's first distinguished lecture of a series over the next five or 6 weeks. My name is James Lewis, and I am on loan from NASA Johnson Space Center in Houston, Texas. And I'm serving this year as ISU SSP's program director. Tonight, we are honored to have 2 speakers. One of them we recorded. He's a 90-year-old Russian, very famous Russian scientist, so it's hard to get him to travel. So we did some recordings and have some Q&A, and we're going to have video of him. And then right after him, I'm going to come back out and introduce James Green, who's a former NASA chief scientist. And these are our 2 guest lecture speakers for the first series. This particular event tonight is called Space Travel Across the Decades and Beyond. The early space race between the United States and the Soviet Union created an era of scientific discovery and innovation. It propelled rapid advancements in spacecraft technology, planetary science, and interplanetary exploration strategies. Despite encountering lots of setbacks, the pursuit of knowledge about the solar system continues. Tonight, Mikhail and Jim will take us on a journey, reflecting on the past and looking forward to unlocking the mysteries of the solar system and expanding our understanding of the universe. First, we're going to welcome Mikhail's pre-recorded lecture video, and then, like I said, he'll have question and answers from his home in Moscow. Mikhail Marov is a department chief in the M.V. Keldysh Institute of Applied Mathematics, Soviet Academy of Sciences in Moscow. He is also a professor of planetary physics at Moscow State University and has been one of the key figures, if not the key figure, in the exploration of Venus through the Venera series of interplanetary spacecraft. So we are going to welcome Mikhail, and then we're going to turn his video on. Thank you.
Good evening. I'm pleased with you, unfortunately, not face-to-face, but online, because it's so time difference. It is about 3 a.m. Moscow time, so it's inconvenient to me. Good evening. To be with you personally. I'm pleased with you, unfortunately. First of all, I appreciate not the invitation. Face-to-face, but online, because it's so time difference. It is about 3 a.m. Moscow time, so it's inconvenient to me to be with you personally. First of all, I appreciate invitation to participate in this event, sharing this distinguished lecturers panel with a good friend of mine for years, Jim Green. This is a short story about Soviet-Russian planetary exploration, and this is just very well fitted to the title of the panel, Space Travel Across the Decades and Beyond. I tried to be concise because of the time difference and because of the time limit. This is outline of my talk. As I said, it will be brief enough, and I apologize in advance being so much concise. Okay, so first of all, a few words as a prelude to this talk. The 20th century will be forever in the memory of the mankind because the humans broke the bound chains and began to explore space around the planet Earth. Soviet Union initiated this process, orbiting the satellite Sputnik in 1957. And shortly after that, the first attempts were undertaken to send spacecraft to the moon and planets. Space exploration emerged as a byproduct of military competition between USSR and USA in weapon delivery systems. Basically, the first peaceful payload for space exploration was just changed waterheads on the missiles. And these missiles were modified in order just to put the payload in the Earth orbit. And competition between the United States and Soviet Union in Cold War produced the greatest adventures in the human last century. We had excellent leaders of the Soviet space program. It was Sergei Korolev responsible for the space technology, and Mstislav Keldysh was responsible for the space science, and this, as I said, the real leaders of the space program. Me was fortunate being involved in our Soviet space program basically since very beginning. And I work especially closely together with Mstislav Keldysh. This is me, still young at that time, because it was just end of 50s, and at the right, Keldysh deputy Alexander Vinogradov. Soviet space science program had and still has 4 main directions. And among these directions, which displayed, I distinguish the solar system exploration, and I will focus my talk on this specific area of space research. First of all, we will start with the moon exploration with the lunar spacecraft. As I said, this enterprise started soon after the launch of the first satellite, and the first attempt was just to launch vehicles beyond the Earth's orbit. And for this purpose, the special upper stage of the launcher was developed. And it was just end of the 50s, and the first Luna 1 and 2 were just demonstration of the possibility to reach the moon orbit. But Luna 3 was extremely successful mission because it was just flyby around the moon, and the first in the history taking images of the far side of the moon. So it was, as I said, really good success. Then the efforts of the both countries, Soviets and the Americans, were focused mostly on the performing soft landing on the moon surface. It was just not an easy task, and several failures just accompanied these attempts. And only in the 1969, it was a 66, sorry, it was the first success with the Soviet Luna 9, followed by the Luna 13 and 66. This is several demonstration of the vehicle's scheme of this landing on the moon surface, and the first photograph, first image, panorama of the lunar surface. And it was extremely exciting endeavor, an extremely exciting science return, because at the first time in the history, we had a chance to see close up the Venus, the moon surface. This first landing, followed by the several satellites, and these satellites took images and basically just mapping of the moon surface. And it was extremely first steps toward taking good pictures of the lunar, not only in terms of the good science, but also in terms of the preparing just the mission, manned mission to the moon. And this was the greatest context, chasing each other of Soviets and Americans to land the first man on the moon surface. Americans was really successful in this endeavor, landing the first cosmonaut on the moon. But Soviets lost this competition, but instead of the manned flight to the moon, it was developed extremely efficient automatic vehicles sending to the moon in order just to return back just samples of rocks, sample return, and also to descend the first in the history moon rovers. This displaying just at the configuration profile of the first station, which landed on the, which not only landed on the moon surface, but also returned soils. And this is extremely efficient, returning back just the probes, just samples, in order just to investigate in the international labs, because it was also exchange of the soils between the Americans, Apollo, taken samples and taken by several lunar missions. It was first in the September 70, followed by the February 72, and finally in 76. And the 76 mission was extremely successful because it allowed us to drill the moon surface to 2.3 meter depth, and preserving the stratification of the soil in the ground. This is exciting time of the returning soil sample, lunar samples, to the laboratory of my institute, Vernadsky Institute. These are the leaders. To the left is the picture of leaders of the program. Me is just in between. And at the right, I'm standing nearby vacuum camera, observing the results of the first investigation of the lunar soil. As I said, it was followed by the moon rovers, and the first landing on the surface of this automatic vehicle was performed in 1970, and then it was called Lunokhod 1, followed by the Lunokhod 2 in 73. They traveled through the moon surface for about 1.5 years and studied vast areas with instrument packages. Lunokhod 1 covered distance 10.5 kilometers and Lunokhod 2 37 kilometers. This is examples of images on the lunar surface taken by Lunokhod 1. This is the tracks of the Lunokhod motion, and these traces will preserve for millions of years on the moon surface. Likewise, the foods of the Apollo astronauts because of very small erosion on the moon surface, and so very good conditions for such kind of features preservation. In Soviet program, especially successful was Venus exploration with the set of Venera spacecraft. The first entry in the Venus atmosphere with parachute descending, it was the Venera 4 spacecraft, which successfully entered the Venus atmosphere and descended through the atmosphere, transmitting back to the Earth the results of the measurements of the chemical composition and the parameters of the Venus atmosphere. We just had no idea what is the real pressure and temperature exists on the Venus surface. So the spacecraft, the vehicle, the lander was just designed for the extreme limited pressure, 15 atmosphere bars. But it's happened that the atmosphere is much deeper, and the vehicle was crashed at the height of about 23 kilometers, and the last temperature and pressure was just as shown here, and the chemical composition was measured, and it turned out that the atmosphere mostly consists of carbon dioxide, in contrast to the expectation of the nitrogen atmosphere. It was extrapolation of these last figures of the temperature and pressure measurements up to the surface, and at the first time it was discovered very hot and dense atmosphere at the Venus surface, with the temperature as much as about 450 degrees Celsius scale and pressure above 90 atmosphere. The first attempt was followed by the second generation of the Venera stations, and this just at the left shown the scheme of parachuting in the Venus atmosphere, just in so-called inverse parachute descending, in order just to measure accurately the parameters of the Venus clouds, and then to descend quickly to the surface in order just to prevent enormous heating of the lander. And the lander configuration profile is shown at the right picture. It was a great achievements of the Soviet engineers, which just developed very good design for the landers to survive on the hot Venus surface. And this surviving for about 2 hours allowed us to transmit back to the Earth, first of all, black and white, and then color panoramas of the Venus surface, which displayed at the left side of this slide. We also, in addition to the several landings on the Venus surface, developed the first in the history facilities in order just and design special spacecraft for the radar mapping of the Venus surface. And it was made with Venera 15 and 16, which mapped with the radar facilities not just northern hemisphere of the planet, followed by the global mapping with the NASA Magellan. But it was at the first time revealed very specific features of the Venus relief and some properties of the surface. The first attempt, and not even attempt, but the first, last missions to Venus with landers were in 1986. It was a special vehicle developed in order just to perform rendezvous with the comet Halley, but to jettison special Venus landers en route to the comet. And that was a quite successful mission in both study Venus and also comet Halley. The image of the comet nucleus is shown at the upper right, and also soon after this mission, it was another partially successful mission to the moon, Martian moon, Phobos. And this picture at the lower right shown here. It was displayed by the imager of the Phobos 88. I very much like this photograph. It's just like the rock flying around the planet. And on board of Vega spacecraft, it was installed small balloons which flied around the planet for about 4 days. And this is some kind of the remnant of the project, very challenging, ambitious project, was developed by us jointly with the French colleague. It's a large balloon, about 16 meters across, the balloon itself, and quite effective instrumental package. This is shown, this French and Russian colleagues of mine in the Toulouse Space Center. As I said, Venus missions were extremely successful, and they brought a lot of the important information. Basically, they just open us, the planet, like completely not like a twin of the Earth, which supposed initially, but a completely hostile world, which not hospitable in order just to visit it. This is the list of the main results, which include not only just a direct parameters, measurements, both in the atmosphere and the surface, illumination in the atmosphere, attenuation of the solar incident radiation, also the measurements of dynamic wind velocity with the Venus atmosphere, which confirm the so-called merry-go-round circulation on the planet. Also, detailed study of the clouds, which turn out composed of sulfuric acid droplets, and also measurements of the composition of the soil and some mechanical properties of the surface, bearing capacity, for example, electrical conductivity of the planet. And also, it was just at the first study of the plasma environment around Venus. We also undertaken several missions for study Mars with the spacecraft. First flights to Mars was undertaken as early in the 90s, and it was just flyby vehicle which not were successfully launched but not reach the planet because of failure in flight problems. Mars vehicles, second generation, were much more successful, and especially this is some configuration in the testing facilities and the vehicle lander itself, the orbiter, and some other interesting design of the lander itself. This is a special attempts undertaken in order just to land perform soft landing on the surface, and it was successfully performed with Mars 3 in 1971. It was the first landing on the Mars surface, and in second launch window in 74, it was just at the first time in the history made direct in situ measurements of the Mars atmosphere. Well, we, in fact, just very much unfortunate with the follow-up processes of the planetary exploration, because the greatest disturbing process occurred in the former Soviet Union is disintegration, and also because of the social economical turmoils which happened in the country. We had undertaken some very ambitious mission with Mars 96 multifunctional spacecraft, orbiter, a few small landers, and penetrators in 1996. But unfortunately, it was a failure just soon after launch, and the spacecraft did not enter just Martian trajectory. Well, we hope for some kind of the recovery of the planetary program with the new Phobos ground mission, and it was just developed in the beginning of this century, first decade, but unfortunately the mission was also failed. This is mission Phobos soil, intended to return back to the samples from the Martian satellite Phobos back to the Earth, and this is just general profile of the spacecraft, its main characteristics, and this is mission scenario. It was just launched, and first of all, just inserted to the Martian orbit, then this approached Phobos, descended and landed on the surface, and then returned back, taking soils in order to deliver them to the Earth laboratories. Phobos soil spacecraft configuration, quite sophisticated design, but as I said, unfortunately, a launch in 1911 was unsuccessful. Also, it was undertaking a project so-called ExoMars, and with scientific objectives of the quite important measurements in both Martian atmosphere and the surface. This project was just joint efforts between between Russia and European Space Agency. And in 2018, it was quite successfully launched at the first part of this program. The first program, it was just satellite, yet it should be followed by the second part with the much more ambitious landing of the Mars rover. and it is intended for the 2024, but unfortunately, quite recently, European Space Agency abandoned this project, and I very much hope it will be developed and successfully implemented by the Russian Space Agency alone. So, what situations right now with the planetary missions, Moon, Venus, and Mars? We have both committed federal program and blueprints. Lunar program, as it's just in the federal program, and this is missions in 2020s and beyond. We are going to launch in this August the first lunar mission of this series, and it will be Luna 2025, as I said, in this August. It should be followed by the orbiter in next year or in 2 years, and then it will be more ambitious and more comprehensive Luna 27 missions. And this is planned for the 27. And in the end of 20s, just at the planned return back to the sample return right now from the polar regions of the moon, not from the equatorial regions, as is what happened before, and also to land lunar and on the polar regions of the moon. This is the scenario of Luna 25, which should be launched in about a month and a half, and which orbiter and lander, as I said, in the polar regions. This is expected results of the lunar globe, which require just return back to the our skill in soft landing on the surface, and also to return quite good science with this spacecraft. We also just developing some ideas, and there are quite, I think, they really quite valid, and in fact, this is the blueprint plans Roscosmos to develop in the 30s after starting piloted mission to the moon, the lunar base, with the configuration as shown here. We also, just in our blueprint, the idea to return back to the Venus investigation with the Venera D mission. This mission, quite ambitious. These components are shown here, and it includes not only long-lived lander, but also deploying of the balloon, long-lived balloon, with the ability to change altitudes from about 40 to 60 kilometers. Also, we are going to return back to the failed Phobos soil mission, which right now called Boomerang, and this configuration is shown in this slide. So, in conclusion, space resulted in the explosion of research and technology and development. And it was just, as I said already, byproduct of the Cold War, with the extremely successful results because it was not only remarkable feats on engineering, but enormous scientific progress for Earth application. It had not been for political imperatives of the Cold War, it's highly unlikely that the national investment required for this progress would have been made. USSR had an ambitious national cooperative program in scientific investigation in the most advanced area of space exploration. The SSR robotic space program was driven by the desire for technological achievement, international recognition. All these things were achieved with robotic spacecraft. Soviets were first on the moon, first on Venus, and first on Mars. This is the book published in 2011 by Springer Praxis, and it was written by myself with my close colleague, former NASA Deputy Administrator Wesley Huntress, and it's called Soviet Robots in the Solar System. Just what I said, first in the moon, first in Venus and Mars displayed in the cover of this book, and this is recognition of the great achievement which was made by my country in these extremely exciting, fascinating endeavors. And finally, some lessons learned and perspective. It's said that despite of the many failures in the Soviet space program, it was demonstrated that planetary scientists and engineers in the Soviet Union and Russia have been working, who have been working with the minimal resources and quite limited support and optimal technologies for many years, achieved a great progress in the planetary exploration, in the study of our solar system environment. Despite this reality, they have enhanced understanding of the solar system in fundamental ways. Phobos Grund, after failure of Phobos Grund, it was written, must be viewed as a part of a long train of mission over the years. I hope it is not the last such mission undertaking. It was written by the famous journalist in United States, David Harland, and I just in great sympathy with this good statement. That's just what I would like to deliver to my talk, and I will be happy to answer your question as already. Thank you. Interstellar space, interplanetary space in the former Soviet Union. The first question from Eric Dankstrom, a good colleague of mine for years. Glad to hear from you, Eric, and I am happy to communicate with you at least by the online. I had several questions after my talk recording the space history or the history of space exploration, interstellar space, interplanetary space in the former Soviet Union. The first, glad to hear from you, Eric, and I am happy to communicate with you at least by the online format. It would be much better to face, but the situation not allow it to do that. Any case, thank you for, first of all, for your comments. And the question was, how was I been able to share those important scientific results while operating under the culture of secrecy, or the constraints of the culture of secrecy within the Soviet space program. What were the challenge? Answering this question I would emphasize three important items. First of all, in my position, in my role of one of the leaders of our space program, space science program, I've been flexible enough. Also, let me say that I've been quite knowledgeable and clever in order not to cross red lines. And it was in satisfaction of the decision makers in the political echelons of the power, and that's just was quite satisfactory for them. Second item, the secrecy mostly concerned technology, not science itself, and some technological details I was not intent to disclose, and also it was not necessary to do, highlighting the most important scientific results which were obtained. And third item, I proceeded from the basic concepts. The science is international, and scientific results are for benefit of the whole mankind, and all breaking through the scientific frontiers are promote progress of the all mankind. And it was convincing enough and met understanding. First of all, people who was our leaders in Soviet Union, scientific leaders in space, Mstislav Keldysh. So that's just what I could answer your question. The next question concerns competition between former Soviet Union and USA. Well, as I already stressed a point in my lecture, in my talk, we were benefited for such kind of the competition driven by the military standards, unfortunately, but it was reality, and it was just allowed us to achieve many important results in space science. Well, I would say also that such competition, and I wouldn't say an attempt to chase each other in the USSR and USA, especially in the program of descent moon on the moon surface, was extremely important, gave some progress in space technologies, and it was extremely important byproduct of this technology development. Okay, do I think that it will be the same in the future? I don't think so. There is no such strong motivation as it was in the last century. And I think that it will be certainly important step forwards in order to break down some new frontiers and dreams in space exploration. But it will be mostly driven by not such kind of the political competition, but the extremely new level of the space technology development. And so we will still witness, I think, especially the new generation, extremely great progress in study of our environment and possibly even in starting steps in the colonization of some solar system planets. So my vision for the near future perspectives. Okay, thank you. Okay, this question is split in three parts. First of all, what was strength and weakness with respect to space of the Soviet academic, economic, industrial, and political system compared to US and Europe? Well, I already partially answered this question. The strength of the space program in the Soviet Union, it was very important governmental support. This support was not only just in the supporting of the industry involved in the space exploration, but also quite a great share of the budget for space, which were going to space science program. And also, and I just experienced this myself, when we were lacking with the funds, we was able to ask government to share at least some additional part. I mean, in addition to the item which was written in the specific fiscal year. And it was extremely important in order just to advance the exploration and to achieve the targets we faced. The second, how the political and and the weakness of this system was in the very limited involvement of the private segment. And such situation, unfortunately, remain until now. We have very limited involvement of the private sector in the space exploration. Second, how has the political and economic trajectory of post-Soviet Russia influenced its space sector? Well, this is very painful question to me. Well, it's very difficult to explain, and especially in the very limited format. But I would say that after the so-called perestroika in the end of 80s, beginning of 90s, last century, we faced extremely tough situation. It was not only political upheaval, but it was social, economical turmoil, and this impacted very badly on the space program. Basically, we just remained our, I would say, at the previous level support of the piloted program. And this still continued, and we have quite well achievements in this area, and specifically in such part of science like the medical biological program. But what is concern of the exploration, planetary and moon and planetary exploration, that was very much jeopardized by the new system which came in the new Russia, and it was not enough attention and support to this segment of space exploration. And we still feel this situation right now. Third, space sector specialists also emphasize the need for international cooperation and so on. Well, that's true. And I think it's absolutely obvious thing. Any cooperation is much better than confrontation. And using mutual resources, mutual skills are extremely positively benefit to the implementation, in particular space program. We have excellent examples of that in the space area. For example, just to mention a few, it was a quite successful program of Mars Express and Venus Express mission with Europe, and it was extremely important first part of the committed program of ExoMars. Unfortunately, we came right now to the very bad situation with such kind of the cooperation. It was not Russian initiative to cancel many program which was committed between US and Europe. In particular, canceled the cooperative program for the Venus exploration, Venus mission. Also, it was recently canceled the second part of ExoMars. Let me repeat, emphasize the point that it's not our initiative, that is very badly motivated by the political situation, not for benefit for science. The second item of the fourth question concerned the situation right now existing in space exploration in USA and China. The question is, could we find an analogy in this competition between USA and China, analogy what was occurred competition between USA and USSR in the previous century? Well, I do not think so. I think this is some kind of the regular implementation of space program. Certainly, there is a part of some kind trying to be advanced in this space science area. But it seems to me not just at the competition, rather this is some kind of the general progress in science. In every part of science, we have such situation when the people try to conquer and to achieve some important goals. And also, this is important that we cooperate with China in many fields of space exploration, and in particular, there is a memorandum of understanding in the setup of the future lunar base between China and Russia on the governmental level. Okay, and the third part of this fourth question. Space has traditionally been viewed as poorly peaceful domain in the past. What I'm thinking about the future? Well, you are completely true. Peaceful exploration of space was just declared in several international documents. And we are still hoping that it will be the real, space itself as the arena for confrontation, for the additional area for the battlefields. But we have, unfortunately, progressively increasing part of space utilization. I mean, space itself, information technology, in order just to be involved in the military process, in the military program. And just what you mentioned, in the current situation, with some very anxious process of the military situation existing in the Ukraine, it's also involve such kind of the systems. And well, I do not think this is for benefit for the further progress in space exploration. I very much hoping that it will be not just increased and in progress in the future. Okay, let me conclude with such statement that I very much appreciate the invitation from the ISU leadership to take part of this important event. I just all my life I did not underestimate the importance to share some important discoveries and progress in science among the wide public. And I think this is extremely important mission of the International Space University, in which I involved as a significant part of my scientific career. Let me again appreciate and acknowledge such kind of invitation and kind assistance of the ISU staff, and I especially benefited to share my involvement with the good
Such a
friend
long
of
period of
mine
time
for
for
years,
history of
with
space.
Jim Green.
I
And
don't think I
wish
realized we had left so
everyone
much material. It was kind of
involved,
longer
and
than I
Jim
expected, so my apologies for
specifically,
that.
all the best.
Next up, we have Jim
and,
Green. He's a
good
distinguished
luck.
NASA
Thank
scientist,
you.
has had a stellar 42-year career before retiring in 2022. He has a PhD in physics. He's worked on numerous missions, held key positions across NASA. Some notable contributions include managing the Space Physics Analysis Network, serving as a co-investigator on the IMAGE mission, and then directing NASA's Planetary Science Division. Jim's accomplishments include over 125 scientific articles, having an asteroid named in his honor, and coordinating NASA's involvement in the film The Martian. So please join in welcoming Jim Green to the stage.
Thank you, James. It's a real pleasure to be here. And I know it's getting late, so we're going to talk about traveling in space that NASA has done in direct competition with the Soviet Union. I'll point out a number of things that have happened, of course, that Mikhail has pointed out. What we really have started with was the Soviet Union's launch of Sputnik. This happened, of course, in the late 50s, and what response that NASA had, or rather the U.S. government had, was indeed to be able to develop an organization such as NASA to respond. And indeed, Dwight Eisenhower, the president at the time, was the real key individual to make that happen. Well, with Eisenhower's term being over and John Fitzgerald Kennedy coming in as the next president of the United States, his goal was well stated, that by the end of that decade, they would put a man on the moon. Not because it is easy, but because it is hard, as he said. A very famous set of words that then set the tone of the U.S. program to be, of course, in a competition with the Soviet Union to be able to get to the moon first. Well, NASA developed a whole series of launch vehicles, beginning with the Redstone, the very successful Redstone series that ended up being the Explorer 1, the launch in 1959 that James Van Allen had his first successful experiment on that Explorer 1, discovering what we now know as the Van Allen radiation belts. And for the ISU students, we'll be talking a little bit more about that tomorrow afternoon in the Space Environment lecture. But indeed, NASA then began to pull together much larger rockets necessary to be able to carry humans into space, starting with the Mercury program, the Gemini program, and then, of course, the Apollo program. Now, what ended up happening that many people don't realize that in this space race, we needed to know enough about the moon to be able to put humans on the surface and then return them, all right? And so even the planetary scientists were confused about what they would expect to see or feel when the astronauts walked out onto the surface of the moon. For instance, we already knew that the moon without an atmosphere for billions of years has been pelted by micrometeors. This grounds up rock like crazy and ends up with the topsoil being what we call regolith. Now, if you look at regolith in very small individual pieces, what you find is it's a silicon rock basically, and it's very jagged. There's nothing on the moon that then will round that. There's no atmosphere, there's no major geological events that occur on such a wide scale that then ends up creating anything but these very sharp, spiky things. And in fact, many of the planetary scientists were so afraid that the regolith had built up to such high degree that an astronaut walking out onto the surface of the moon would go up to his chest in depth, in regolith. So we had to find out what was going on. This meant that the science program, the planetary science program, was going to kick into high gear. Now, what I'm going to show you is a little film that has at the very top those missions up to 1976, the early part of the space program, that were meant to be as flybys, then orbiters, then landers and rovers down on the surface. Okay, so that'll be divided in this way. And what you're going to see is the large number of missions that are occurring. Now, what's really exciting about this is that early on, the first 4 NASA missions were total failures. I mean, we couldn't even hit the moon. You know, we tried very hard to just have a crash landing, flew right by it. I mean, what is that all about, right? And in the meantime, we're also kicking into high gear, going to different places, flying by Venus, flying by Mercury, flying by Mars for the first time. And many of those early missions were also unsuccessful. Well, as you saw, the large number of missions that occurred that were testing the moon really led us to the opportunity to say, we know enough about the moon, we believe, to land safely on the surface and return humans. And that ended up being, of course, the Apollo program, for which we had 6 successful landings. Now, you may not remember this, but indeed, Neil Armstrong's very famous step out on the moon wasn't the first thing he said. What he said when he opened the door to then start down the ladder is he looked around and to see how deep in the regolith the pad that the lunar limb was on sank into the surface. Okay? Because once again, the controversy was maybe there was so much regolith that it would be subsumed in at least a foot or so each of these pads with regolith. Wasn't the case. He said the pad sits strongly and firmly on the surface, and then he exited, turned around, and walked down, and it was one giant leap for mankind. What we learned from the Apollo program was absolutely unbelievable in terms of knowledge about the early Earth and moon formation. We brought back more than 380 kilograms of lunar material. Now that's regolith, that's cores, and that's rock samples. And studying those in the laboratory was a gold mine of information. We found out that the composition of the moon, including what we call isotopes, which are variations of the natural elements, and that of the moon and the Earth were the same. So that means we were formed at the same time. The oldest rocks on Earth today, you can run around, you can find them in Australia, and there's a couple other places, are only about 3.8 billion years old. The lunar rocks are 4.5 billion years. So Where did the 700 million years go? Well, it turns out the Earth's atmosphere really does a number on modifying the land. Our climate has done nothing but change over the 4.5 billion years since our creation. And there's plate tectonics, there's oceans, there's weathering. All those effects eliminate the oldest rocks on the surface. So by going to the moon, we found the age of the Earth. Also, we realize that the impacts that we see today, we know these craters are impacts, but at the time, we thought, well, those are just caldera of volcanic material. We don't see that kind of impacts here on the Earth. And if there's things that are impacting the moon, why wouldn't they impact the Earth? The Earth is even bigger than the moon. Well, it turns out, for every one crater on the moon, which are impacts, there's 20 of that size here on Earth that have occurred. All right? Where are they? Well, once again, our climate has changed. The surface has changed. Those things have eroded. Impacts occur in the ocean. You never see them. And that is what's really changed our thinking about how the Earth and Moon evolved together. And so that early history of the Earth and Moon was extremely important. Well, when the Moon was formed, it actually was formed very close to the Earth from this huge impact that occurred that brought two big objects together, the proto-Earth and the proto-Moon, slamming together, reforming into two objects, one called the Earth and one called the Moon. Well, it put the Moon very close to the Earth. And now we know what's happened. The Moon moves away from the Earth about 2.5 to 3 centimeters a year. A year, okay? And it's been doing that for billions of years. So the knowledge of the Earth and the Moon was so well demonstrated by the Apollo rocks that many of those samples are still being saved and analyzed today. There's at least 60% of those samples that we really haven't interrogated. But as we learn and ask more questions, we'll go back into the rock sample. Well, after the Apollo program, the major shift was really building the shuttle. The shuttle was designed to build the International Space Station, to really begin the process of looking at what's happening in low Earth orbit. If those scientists and engineers out there can think of all the equations that include a G, which means gravity, and then make that 0, that changes the equations enormously. And so what happens in what we call microgravity in terms of how fluids are formed or crystals are formed? What does fire do without gravity? What happens to the human body as it floats weightlessly in space? And how does that bode well or not well for space travel well into the future? Those are the questions that we answer up on the International Space Station. And now we're bringing more commercial groups to be able to come up and make pharmaceuticals. Even grafting skin is easier to create skin in orbit than it is here on Earth. There's so many other things that can be done now in low Earth orbit that we're just beginning that process of understanding what we can do. And of course, space station is a real marvel. It's got all kinds of stuff going on from experiments, life science experiments, crystal experiments, et cetera, human experiments that are going on, understanding how the space station radiation environment is different than that of beyond Earth, because we need to know that if we go to the moon and then on to Mars. What about the other part of the program, the earth science and astrophysics and heliophysics part of the programs? They haven't been dormant. They have absolutely exploded. These are just a list of the current Earth science satellites that are in space or being developed to go in space in the next couple years. NASA has well over 100 missions going on. And what we know from these missions and the previous ones is really a lot about how the climate on Earth is changing and what that means in terms of the temperature increases that we expect from those changes, because that's what's happened on Venus. We're recognizing that what happens on some of our planets can happen on Earth. And that includes Mars. What's happening on Mars can also happen on Earth. So this is just an enormous area for research. Now, we want to know what's happening between the sun and the Earth. This is what we call space weather. The sun goes through sunspot cycles. It constantly outgasses. This affects all our systems, our spacecraft, but also may have the opportunity to generate huge amounts of radiation that could be a problem for human space travel beyond the magnetosphere. And then, of course, our astrophysics missions, where we're looking beyond the solar system, out into the galaxy, looking at stars and exoplanets, looking at other galaxies, looking at new things such as dark matter and black holes. These are the things that are being really pursued in the NASA astrophysics program. And then in planetary, there's been a huge push to do the same thing with Mars that we did with the moon. NASA launched more than 20 missions prior to the Apollo to learn everything about the moon before we set foot on the moon, and we're doing that now with Mars as an example. And here's an overview of all the NASA missions, both current and past, and a few in the future, for which the X's indicate the ones that have failed. And so we have failed at Mars. And when you look at this, all the international programs put together are going to Mars, we see about 56 missions for which about 25 of them have failed. We're right just a little past 50-50 in terms of our chances to have a successful mission to Mars. I mean, Mars is hard, and there's a variety of reasons for it. But now we understand enough about it to really, I think, internationally, do well on the red planet. Well, NASA's also done a couple other fantastic things. Just like the Soviet Union, we have developed radioisotope power that enables our spacecraft or rovers to go to places where the sun doesn't shine or shines so little that we can't power our spacecraft. And these radioisotope power sources and capabilities that we have enabled exploration of the outer part of the solar system for NASA. So that includes Jupiter, Saturn, Uranus, and Neptune, also Pluto, and then, of course, 4 missions right now have penetrated what we call the heliopause. That's the extent of the sun's magnetic field, and then it plowed through that region out into the space between stars and are actually making measurements of winds of other stars. Now, Pioneer 10 and 11 are dead, so they're not contributing to our knowledge of that, but Voyager 1 and 2 are now outside our heliopause, now making those measurements. So it's fantastic measurements of what's happening between the stars. So this, I think, is the basis of a huge number of things that are going on in terms of our ability to leave the bounds of Earth, explore other planets, live and work on those planets, and return. Webb has launched and is making fabulous discoveries. This particular telescope is enormous. It's more than 6.9 times the size of Hubble in terms of its mirror. It has tremendous collecting power in the infrared. It actually measures heat that's generated by the planets, heat that's generated by stars and nebula, and we're actually looking at spectra of exoplanets right now to determine if their atmospheres are like ours and where they are different, why they are different. So it's making an enormous number of really important discoveries almost on a daily to weekly basis. Of course, I want to talk about the Artemis program. This is now the next push that NASA has of returning to the moon with a very large space launch system. This is 10% more powerful than the Saturn V that took the Apollos to the moon. And it has the capability to then also go on to Mars. Well, of course, what's happened recently is the Space Launch System with the Orion capsule, uncrewed, has made its first launch this last year and was tremendously successful. And here's the path that it took, launching, going out, doing a figure eight around the moon, being out into interplanetary space as a space system that will have humans aboard in Artemis 2 in a way that we've never done before, and then indeed back to Earth. So this was tremendously successful, and we're now gearing up to the second part of that, which would be the Artemis 2 mission. Now, in addition, Artemis 1 also had an array of scientific instruments that it took and sub-satellites that it threw out all over the place, many different CubeSats. So what about the future of the program? Well, as I mentioned, the key in the Artemis program starts with Artemis 1, which has been successful. Next year, we'll launch Artemis 2, which will have nearly the same path, but not exactly as Artemis 1, but it will be crewed. It will be our test of all the subsystems. That will lead to Artemis 3, which will end up with humans stepping down on the surface of the south pole of the moon. This will be the first woman, and the second person will be a person of color walking on the surface of the moon in a really unique place, the south pole of the moon. It also talks about a number of the other scientific experiments that will be accomplished between now and when Artemis 3 will occur. And that's shown here. These are many landers. There's also additional orbiters. Most of these are commercially being developed, for which NASA is buying the ride, and they are developing these systems right now. And so it's a very exciting time to bring in our commercial partners in a new and unique way as we share the opportunity to go into space. And so with that, let me thank everyone. I think it's been an exciting opportunity to listen to Mikhail, who was, I have to tell you, one of the pioneers of the Soviet program. As a scientist, he's literally been involved in virtually everything they've done since the late 1950s. So thank you very much. I know that was pretty quick, so you may have a couple questions, and then we have a reception, I believe. So let's, whoever's bringing the mics around, we have some hands up. Okay.
Would you please say some results that we can see or something about Voyagers?
The Voyagers?
Yes, now that they are
Yeah.
far from us.
Right, so what we're finding out is as we have punched through the heliosphere, this is this protected magnetic bubble that exists around the sun, we're seeing that the cosmic ray flux has shot up. So this tells us that our magnetic field from the sun has been protecting the inner solar system from even worse cosmic rays than what we would see if we traveled between the stars. So we want to be able to understand the environment, and the Voyagers have started to do that. What's happening is that has rippled into the astrophysics program. We call heliospheres of other stars astrospheres. And we're now beginning the process of looking at those astrospheres, how they expand, how they contract, because that might help understand the habitability of planets that are orbiting those stars.
Thank you.
Sure.
Hi, thanks for the talk. It was really, really cool. My question would be, from a scientific community perspective, what are the capabilities and mission you think are most exciting right now, and what do you think are the capabilities, technical capabilities needed to realize that?
Yeah, our scientific cadre of missions extending from astrophysics, Earth, heliosphere, and planetary missions are spectacular. And indeed, every mission builds on another one. In Earth science, we're doing original research on studying the changing climate of the Earth and how the Earth changes over time in many other ways. Sea surface salinity, also the distribution of water on the Earth, and just many of those things. And we're now making those really tough measurements that give us the aerosols and the really what we call trace gases that are occurring that do indeed absorb heat, They're greenhouse gases and affect the warming of our planet. Well, that is also being carried into our planetary program. Some of the things that we're doing on Mars is done in a very similar way. But now on the ground, we're actually making fantastic measurements of the chemistry of the surface of Mars. So we know that there's carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur in the soils of Mars, and that's everything between my two fingers, okay? And therefore, it has all the right stuff that perhaps it has generated life in the past, and we're going after that. By coring rock and bringing back the rock record, we hope to be able to find evidence in the mineralogy that life may have existed on the planet Mars. So that's just a little taste of those items.
With the developments of the first commercial deep space missions like Capstone and all the landers going to the moon, do you think the focus of NASA is progressively going to move over to that side, or is it going to stay with large traditional missions like James Webb?
Yeah, NASA's been moving into CubeSats for quite a while, and that works really well in and around the Earth area, not so well in planetary. And the reason why is the further you are away, the bigger the dish you have to radio back. So if you can imagine a CubeSat, you know, which is about this big, maybe this long, with a radio dish this big, that doesn't work, okay? And so we're not gonna send back a handful of bits a second, so we have to create an infrastructure for which, as a larger satellite goes, it has these CubeSats that we drop off, and then the CubeSats make unique observations and radio back to the mothership, and then that is relayed back home. That actually is the structure of communication that we use on Mars. None of the rovers have trailers with big dishes on the back of them. It actually radios up the information that is made from the data that it's getting on the surface to orbiters, and then the orbiters send the data back. So we already have a good relay around Mars. That means we can support CubeSats by dropping them off at Mars, and we are starting all that process. Okay.
Okay, I have the next question. So I think given that the South Pole was chosen in part due to the polar ice that's there, how much do we actually know about how we would extract that ice? And then as perhaps a second parter, using that ice as like an in situ resource to generate fuel or other resources, water to drink, etc.
Yeah, we're just coming to the realization, based on the lunar samples that we brought back, that the moon had a magnetosphere early on. In addition to that, huge impacts occurred on the moon, blowing away a significant part of its crust, allowing lava to pour in from the mantle, bringing up all sorts of gases. With a huge magnetosphere of the moon, and outgassing from these impacts, we now believe the early moon had an atmosphere. That means material from volcanoes can move to the poles and snow out, just like they do on Mars, just like they do here on Earth. And so what's sitting in the permanently trapped regions is not just water. It's not just things from comets. It's not just things from meteors. It is indeed from the atmosphere of the Earth. Also, the magnetic field of the moon would be connected to the Earth over certain periods of time, allowing the early Earth atmosphere to come to the South Pole. So, what do we want to do on the South Pole? If you ask a scientist, the first thing they're going to say is we're going to core it. We want to know the history of the early Earth and the early moon, and it's sitting there in these permanently shadowed regions and in that record over time. And what we'll find is we'll find carbon monoxide, carbon dioxide, sulfur. We'll find all kinds of things that were in the volatiles in the early Earth and moon atmosphere that we then also can use. It's not just water.
Thank you.
Hi, I'd love to hear your thoughts on what you think the cultural impact of
For example, finding biosignatures on extrasolar planets or microbial life maybe under the surface of Mars? And maybe what does that imply for the future of our civilization?
So, of course, NASA's planetary program, which I headed for about 12 years, was really all about searching for life beyond Earth. And we made an enormous number of measurements and have made significant progress in that particular area. Right now, we haven't found evidence, either in the planetary program or in the astrophysics program, which are looking at exoplanets, that there is life beyond Earth, you know? We haven't found that evidence. But if you ask me on a personal basis, it's there. We just need to be smarter, look harder, and keep at it, and we'll find it. And I think that will be the discovery of this century. It will be a world-changing event, just like Copernicus saying the planet's moving around the sun and not everything moving around the Earth.
Hi, and thinking about climate change and our future here on Earth, do you think it would be easier for us to make Earth, sustain Earth livable for us, or to go to other planets in the next 50 years or so?
So Earth is our home. It should remain as such. We have to take care of the Earth. But how do we take care of the Earth? Has to be a cooperative effort between all nations, because we all breathe the same air. We're all living in one atmosphere, all right? That's very hard to do. For us to be able, I believe, to survive together on this Earth, we're going to have to enter a period of time where we'll have to engineer the climate. We'll have to make major changes in the climate for the good of the planet and the people that live on this planet. Now, I say that, and then I say also, we're not there yet to do it, and we don't know exactly how or what we would do, but we have a planet called Mars to practice on. We also have a planet called Venus to practice on. In 800 to 900 million years, the sun's energy is going to increase such that that amount of flux that Venus gets today, we will be getting here on Earth, and we will be looking like Venus if we don't do climate engineering. So we have to figure out how to do that. We have a solar system that we actually can learn from, and that will save, I think, the human species if we do it together and do it well. All right, I think that was the last question I was asked, so thank you very much.
Again, thanks to both of the speakers, great information. Obviously, we'll have a chance to see Jim a couple of times this week during the core lectures. I believe the only last point I wanted today is Monica going to come up and say something? Oh, there she is, sorry. And I'll let her close us out.
So thank you, James, for giving me the floor. And I ask license for our SSP participants to speak a little bit in Portuguese with our audience. Can I? Ok, thank you. So, muito obrigada a todos vocês que vieram aqui prestigiar esse evento nesta noite. Vocês tiveram a oportunidade de assistir uma aula que normalmente é fechada dentro da programação do SSP para os alunos do SSP. E nós pedimos na organização local para que essas palestras especiais forem oferecidas em espaços abertos para que o nosso público local pudesse se beneficiar com elas também. Então, muito obrigada a vocês por terem vindo, por terem prestigiado esse evento, espero que tenham gostado. Nós teremos vários eventos como esses abertos. Então, na próxima semana, nós teremos o painel de astronautas. À tarde, esse painel vai acontecer na Farmaconde Arena, para crianças e jovens. Então, vai ter tradução, porque é para um público mais infanto-juvenil, e à noite, aqui, nesse mesmo auditório, nós teremos o painel de astronautas em inglês, para um público mais especializado como vocês. Tá bom? Então, a gente espera contar com a presença de vocês ao longo dessas 9 semanas, nas atividades que vão ser oferecidas. Os detalhes da programação vocês podem acompanhar no site do SSP, então, ssp23.isunet.edu, ok? E nas mídias sociais também, que nós iremos anunciar toda semana. Tá bom? Então, mais uma vez, muito obrigada. Uma boa noite a todos. Thank you so much. Good evening. Have a good rest. Okay? See you tomorrow. Bye-bye. Thank you. Okay. Obrigada.